All right, so third speaker of the morning is one of the other co-organizers, Anders here in Stockholm, on some Cubical Agda.
Yeah, okay. Thank you, Peter. So this talk will be a bit different from the other talks this morning, so there won't be any analysis, but more another interest of Erik, which was formalization of mathematics in type theory. So yeah, so Erik did a lot of great mathematics, as we've already seen, but he also formalized a lot of it in systems like Agda or Coq. And in fact, his last paper, from type theory to setoids and back, which we heard a bit about yesterday, and I think we'll hear more about it in Mill's talk tomorrow. So this is about a formalization of a setoid model of Martin-Löf extensional type theory with universes in Agda. So when I was preparing this talk, I was going through some old emails from Erik, trying to find the source code of this project, and I found this email from last year, end of Swedish summer in August. So he wrote me and Guillaume Marie asking us to check whether his formalization type checked on a new version of Agda, and this v model all rules.agda file contains, essentially imports all the important stuff, and type checking should take like 10 minutes. So we did, and it didn't really work, but so what I did yesterday or the other day was download this archive and unpack it and look at like how much code did Erik actually write for this project. And it turns out it's about 16,000 lines of code. So if you've done any formalization in Agda or a similar system, you know this is quite a substantial bit of coding. And so Peter de Beer mentioned that this was like the knitting project of Erik yesterday. So if he would have knitted same time it takes to do write 16,000 lines Agda code, we all would have a lot of sweaters and socks, I think. This is a pretty impressive formalization, and I'm quite impressed that he had the time to do all of this in addition to, you know, all the other math he did. So it's a very kind of impressive work, I think. Okay, so right, so this talk will be more about formalization in Agda, but in a slightly different variation of Agda, which is this cubical version. So as we heard in the talk by Steve yesterday, homotopy type theory is this new foundation of mathematics, initially developed by Felix Mendel, Vladimir Vovolsky, building on many ideas developed by various people, and Erik had a very influential, lot of influential ideas, like the development of connecting type theory with higher category theory and homotopy theory. So what one thing HOT offers, in addition to many other things, is an alternative to setoids, essentially, or maybe a complement to setoids. If you watch Peter's talk today, one can also like analyze setoids nicely using HOT techniques. So this setoid, so the alternatives that we get from HOT are both useful for formalization, and I would argue for doing constructive mathematics. So that's essentially what I'm gonna, like the theme of this talk is kind of exploring what you can do using homotopy type theory for formalizing and developing constructive mathematics without using setoids. All right. So for those of you who are not familiar with homotopy type theory, let me just point to the two main innovations. So one is the univalence axiom, which in a slightly simplified form essentially says that for any two types A and B that are equivalent, so you can think of equivalence as just being isomorphism in the sense that you have maps going back and forth that cancel. We get a triple bar equality or a path or an inhabitant of the identity type. So there are different ways to interpret what this this symbol means, but you should think of it as, you can think of it as propositional equality, or we'll see, you can also think of it more topologically as the type of paths between A and B. All right. So that's one thing it gives. So it gives some way of converting isomorphic types into, so isomorphism of types into some form of equality of types. All right. And the other innovation are these higher inductive types. So these are types with so-called path constructors. And this lets us define things like quotient types. So here's an example. So we take a type A, and we want to quotient it by a relation R. And then we just write the data type in Agda, or this is Cubical Agda code, where we have some kind of injection constructor that takes an A and gives you something in the quotient. And then here's the new thing. So you have an equality constructor, EQ, which for any two A and B that are related gives you an identification of the image of A and the image of B by this injection map. This is like kind of how you would expect quotients to look if you could write them down as a data type like this, maybe. So, and the new thing is that that homotopy type theory gives us kind of a structured way or a kind of semantically justified way of adding these kind of data types to type theory. Okay, and then you also need to have this squashing constructor, which kind of forces the type to be a set in the homotopy type theory sense, which means that it satisfies this uniqueness of identity proofs. So this is what HOT gives us, but in the standard formulation of HOT, like in the HOT book, all of this is added axiomatically, which then kind of disrupts the computational nature of type theory. So in order to give them computational content, me and my many coworkers have been working on various cubical type theories. So these are type theories based on ideas from cubical sets, which is just kind of a cubical variation of simplicial sets. So instead of simplices, you start with cubes, essentially. And these are good for giving computational content to both univalence and these higher inductive types. All right. So that was intro to homotopy type theory. So let me say a few more things about cubical type theory and cubical Agda. So cubical Agda is this cubical extension of Agda with various things from cubical type theory. So in particular, we have let's say a formal interval type, bold I or big I, which we use to define this triple bar equality relation. So this is just the type of paths between A and B. And a path is just like a normal topology or homotopy theory, a function out of this interval into the type. So an equality of types will be a function from the interval, a path between types will be a function out of the interval into the universe of types, which has the correct endpoints. All right. So that's first thing that cubical Agda adds, this interval and path types. Then there are a few more things. So transport, you can think of it as some kind of algorithmic way of rewriting goals or changing things. Like if you have a path between X and Y, you can kind of replace all the X's in your term by Y. So and this is done in a purely kind of algorithmic or constructive way, right? And then also univalence is proved using something called glue types that I won't talk more about, but they're there. And then also these higher inductive types. Yes. So by adding all of this, we get a proof assistant with all of Agda's features still there. So advanced dependent pattern matching, which also works for high inductive types. So this is very nice. And then all the other Agda features are still there, which is really nice because all of the Agda users like Eric could have tried out cubical type theory very easily by just putting a flag at the top of their file saying it's a cubical file, and then they can use all of the cubical machinery. So that's a big plus for us developing cubical type theory because we get a lot of users for free. With all of these many users that we have, we've developed quite substantial library. So we have 39,000 lines of code. And if you remember, so Eric had written 16,000 lines of code himself. So it's really like compared to this project, which has 47 contributors, his formalization was really substantial. Like here you get a feel for what 16,000 lines of code really means. So, and then, well, of course, not all of these 47 contributors contributed a lot, but still it's like, yeah, very substantial formalization done by one person. So this library contains various things. This thing called synthetic homotopy theory, which is a way to define spaces as these higher inductive types. So for example, the circle, and you can compute homotopy groups, also compute cohomology groups and other things like that. So this we have formalized, and there's also now a growing kind of sub-library of constructive algebra and some computer science stuff like data structures and algorithms. So this, yeah. Yes. It's worth emphasizing that many of the proofs that we do, you can also do in HOT, so standard homotopy type theory, but the proofs often turn out to be simpler with all the cubical machinery, so it's pretty nice. And also everything is fully constructive in the sense that we can just run any program or proof that we write. So we just type things in and tell Agda to evaluate them for us, and Agda will do it. All right. Great. So what am I going to talk about today? So it's the little background about the context of the work. So the work I'm going to present today is joint work with Carlo and Julie and Evan Cavallo at Carnegie Mellon, and Max Zoyner here in Stockholm, who's my PhD student. So we've been looking at how to do set level, so constructive mathematics and computer science in Cubical Agda without using setoids. And of course, people have formalized this kind of mathematics and type theory before without using setoids, but we want to look at things where you would typically use setoids, like quotient types or function extensionality and stuff like that. So we're kind of focusing on set level constructive mathematics and computer science, which you would typically do with setoids, but which we now try to do without setoids, and we'll just see how it is. Yes. So we focus on two problems. So one is a thing called program and proof transfer, which is kind of a by now quite old problem in like proof assistant technology kind of. So you want to very often you want to write programs and proofs using one type, and then you want to transfer it over to some other type. So I'll give examples of this in a minute. And another problem is a classical computer science problem, which is the problems of representation independence. So typically you have some abstract interface, like an interface for finite multisets with some operations, and then you want to relate different implementations of this. And so we also looked at those kind of examples. And to solve both of these problems, we need some cubical version of the so-called structure identity principle. So that explains my title. All right, so let me give an example of this first problem. So what could it mean why would you transport programs and proofs from one type to another? So there's this, so you can have so when you look at different types in type theory, some are proof oriented and some are more computation oriented. So for example, unary numbers, so numbers generated by zero and successors, it's just like piano numbers. They're very nice for doing proofs because, well, natural number induction is what you expect. You get it for free and so on. So everything kind of, yeah, so it's very easy to develop proofs for these unary numbers. But on the other hand, they're terribly inefficient to run code written with them. So for that, you want to use maybe binary numbers. So it's just lists of 0 and 1 with no trailing zeros. So there are these kind of two different ways to represent the natural numbers. So there's some kind of tension when you're formalizing a library, and when you're formalizing something, you have to make a choice. You can't just, you have to choose which definitions are you going to work with, and then you're going to formalize your whole library. So how do we kind of get the both worlds? And this is actually something that was already mentioned by Dijkstra in one of his many famous short notes. So Dijkstra said, so we know that a program must be correct, and we can study it from that viewpoint only. We also know that it should be efficient, and we can study it efficiently on another day, so to speak. But nothing is gained, on the contrary, by tackling these various aspects simultaneously. This is what I sometimes have called the separation of concerns. So we want to have some kind of separation of concerns when we're formalizing mathematics and type theory. Okay, so let's make this even more kind of precise. So let's say you want to prove a goal in Agda that looks like this. So you want to do 2 to the power of 30 plus 2 to the power of 30 equals 2 to the power of 31, right? That's definitely true. And you want to just, have Agda prove this for you. So what you would typically do is you would try to plug in the term refl, which is just reflexivity for equality. And using definitional equality, Agda would normalize both sides of the expression and see that they're the same. Well, if you try to do this, your computer will crash if you're using unary numbers, because, well, these are going to be a lot of successors on both sides. So that is a bit disappointing, maybe. So what we really want to do to solve such a goal is to somehow transport it to the monoid structure on binary numbers, to be expressed using the monoid structure on binary numbers, and get a goal that looks somehow like this. So you have 1 followed by 30 zeros, plus in, which is the binary, plus, like plus for binary numbers, 1 followed by 30 zeros equals 1 followed by 31 zeros. And now if you plug in roughly in this goal, it will terminate in no time because, well, it's just list with 30 elements, that's nothing. So it's very easy to solve for the computer. So this is what we want to do, and we want Agda to do this kind of transporting the goal and replacing all the operations by the efficient ones and all the concrete terms with the efficient representation. So how can we do this? Yes, so to do this, we need to construct a path from the monoid on unary numbers to the monoid on binary numbers. So it's kind of important. So it's not enough to just have a path between unary numbers and binary numbers. We really want it for the monoid structures on these types, because we want to replace both like these terms and the plus operation. And the plus operation is part of the monoid structure. Right? So, so this is, yeah. So let me kind of make this a bit more precise. So you can define monoids your favorite way, for example, like this. So monoid is just a sigma type with some X in the universe of types with some monoid structure. So the monoid structure can be represented as a record or another sigma type with a unit element and a binary operation and standard loss. So then the lemma we need to do, what I did on the previous slide, is the following. So for any two monoids M and N that are equivalent as monoids, we get a path. So this looks a lot like the UA univalence thing I showed before, but here's monoid equiv instead of equivalence of types. Right. So, so if we had this, we could solve the goal on the previous slide. We could also do much more because we get a path here between the monoid M and the monoid N. We can in fact transmit any proof of a property from M to a proof of that property for N. So it's not just like equations between closed terms, but really anything we prove about unary numbers, we can get for binary numbers. So very nice. It's very desirable property when formalizing mathematics. So like I said just now, so this thing kind of looks like this UA term that I showed you before, but and we can use UA to prove it. But once, yeah, maybe we want to also like consider some commutative rings or I don't know, R modules and other structures like that on types and have similar results for those. And the more complex your structures get, the trickier it gets to do it by hand. I mean, it's always possible, but it gets really annoying. And you see, when you've done it a bunch of times, you see that you're doing the same thing over and over. So there must be some kind of general principle underlying this. And this is exactly what the structure identity principle gives us. Okay. So, so one way to formulate the SIP and kind of informally is the principle that reasoning about mathematical structures should be invariant under isomorphism of structures. So it's like a classic, maybe philosophical way of stating it, right? So, but when we're working in type theory, we have to, like when I'm doing a concrete formalization, I have to make this into a formal statement in the theory. And there are many ways to do that. So I listed a few here, or the ones top of my head. So how you can formalize this principle in type theory. So the first version, I think it's due to Peter Axel from 2012 from a talk. Then Thierry and Anders Danielsson wrote a paper, Isomorphism as Equality, and this was then kind of generalized to kind of a category theoretical version, which made it into the hot book. And then there has been a lot of work in this direction, doing different variations, setting things up so that they're more convenient for doing some things and so on, and also generalizing things. And yeah, so some of these are more categorical, like the hot book version, and the Arens Lumsden version is really expressed using category theory, while others, like the Danielsson and Martin Scarlett's version, are expressed more type theoretic language. All right, so there are many different structure identity principles that we could formalize in Cubical Agda, and we ended up settling for the version of by Martin Escarda from his excellent lecture notes on Universal Foundation of Mathematics in Agda. So all of his notes are formalized in Agda, which is kind of nice when you want to port something to Cubical Agda. And also his variation is very type theoretic. And like I said, it's already formalized in Agda, so it's natural to turn into a Cubical Agda version. And another point which I think is very important, which is also supported by other versions of the SIP, is that it's very modular, in the sense that if you have a very complex structure, like, I don't know, an R module, for example, which is built out of many different structures, then you can really decompose the proof and prove, decompose the proof and prove it for all the small pieces that go into the structure. So it's really kind of a divide and conquer approach. And this is, I think, turned out to be surprisingly important to make formalization with this practical, because we can actually automate almost all of the proofs whenever we consider a new structure. So let's say someone wants to add, I don't know, vector spaces, then they just kind of have to give the definition of a vector space, and then they say, tell Agda to generate the proof of the corresponding instance of the SIP for them. And this will be done automatically using reflection in the library. So it's pretty nice that it's automatable. Right. And so, like I said, so we based our formalization on Martin's version, but then some key definitions are changed to be more kind of cubical. And this leads to some shorter proofs. All right, so let me explain what this Martin's SIP looks like. So first of all, we need to say what is a structure. So structure is just a function from type to type, so from the universe of types to the universe of types. And then you take the sigma type of this and what's the type width structure, right? So the total space of this map. So type with S structure, types with S structure. And then you need a way to say when an equivalence of types is structure preserving. And this is just another family of types over the type of equivalences of the first projections of these. So like the underlying types of the structures, which equivalences on the underlying type of structures to preserve the structure. So for example, for monoids, we take S to be this monoid structure, and the iota just says that this, that the equivalence preserves the structure. So it's really what I mentioned before. It's the same pattern. And then we add a little bit of notation. So A is isomorphic to B. If we have an equivalence between the carriers of A and B, and which satisfies iota. So with this, yeah.
Can I ask a quick question there, which is,
yes,
is this in some sense essentially single sorted in terms of algebraic series, or can you easily extend it to deal with multi-source?
Right. So the way it's done, it's not so easy to. So it's not directly multi-sorted, but you can. There's a variation which I might mention in the end where you.
Okay. Thanks.
Yeah. So right now it wouldn't work perfectly for vector spaces, I think, for example, but for many other structures it would work fine. Right. Yes. Yes. So that, okay, yes, thanks for the question. So we end up with this kind of, we have the S and we have the iota, which is a structure preserving notion of like which equivalences are S structure preserving. So then the theorem we want to prove once and for all is this kind of map from isomorphisms of A and B to structure preserving isomorphisms to paths of A and B. So now we can't prove this in general because, well, we haven't said anything about what S and iota is. So we need some kind of condition on this for this to work. And if you're kind of fluent in homotopy type theory, you see that, okay, this is an equality of sigma types. So we're going to need an inequality of the first projections and then a suitable path over. If you don't know what a path over is, don't worry, it's not super important. But so for the first projection, we can just take UA of the underlying equivalence. That works fine. But then for the second part, there's nothing we can do at the moment. So this kind of motivates a notion of univalent structure, is one where iota is equivalent to the following path over. So this is how you write a path over in cubical type theory. So it's really a path between the second projection of A and the second projection of B over this UA, over S applied to this UA of E proof. And that's exactly what we need to give this path up here. So, so this is kind of very simple definition. And Martin has something very similar, but because he's working in hot UF, he can't use path P. So he has another notion which we call the standard notion of structure, which turns out to be equivalent to our notion, right? So this is really where we deviate a little bit from Martin and get something which is more cubical. So with this simple definition of what a univalent structure is, we can very easily prove the thing on the previous slide as follows. So we're defining a path in a sigma type. So it's going to be a pair. And the first part is UA of E, and the second part is just extracting the thing we need from the assumption. So this is kind of, might look a little silly because we solve the problem by just kind of defining it away or assuming what we need, right? So just push the problem away. So because now, like, to prove this, we need to know that things are univalent structures. So that's really where the problem is now. Luckily, this is where this modularity of the whole approach comes in. So let's say we want to do this for monoids now. So we need to prove that monoids, the monoid structure, which I didn't show, but you can believe me that it's equivalent to this kind of thing where you have a raw part, which is like the data of the monoid, which is just a neutral element and the binary operation, and then a predicate saying when such a pair is a monoid, right? So any monoid can be written like this. And then Martin proved for his standard notion and structure, and we prove for our slightly different univalent, but equivalent univalent structures that constants and function types are univalent, and that these are closed products and adding prop value axioms, and actually many other things, but I just listed these because these are the ones you need to realize this, to see this corollary. So because they're closed on the products, we just have to, like, okay, they're closed on adding prop value axioms. So adding this is monoid axioms is fine. And then it's closed on the products. We just have to check that the constant and the function is, and that follows from this theorem. So in the end, we get the theorem we need for monoids, and when we can solve the goal that I showed you before. And like I already said, so this kind of applies to many other algebraic structures, and they follow exactly the same pattern. So all of these proofs are fully automated in the library, which is kind of neat. Okay. So now let me quickly speak a little bit about the other problem that we've looked at, which is this representation independence problem. So this was stated as followed by Mitchell in a Popple paper from '86. So problems should not depend on the way stacks are represented, only on the behavior of stacks with respect to push and pop operations. This really is kind of a guiding principle in good library design as a programmer. Like if you design some interface, any code you write using the interface shouldn't really look under the hood and do anything bad. That's essentially what it says. So in computer science, it's very common to consider structured relations between types, which are weaker than isomorphism. So we'll see an example on the next slide. So there's plenty of one-to-many and many-to-many correspondences there. And there's a whole wide range of there's a whole theory of this, which is like the realm of parametricity theorems. So this is like a big part of computer science literature. It's about studying relations that are respected by quantification over structured types, right? So now the SIP that I showed you just a minute ago lets us identify isomorphic structure types. So what we then started wondering, like, what can we do about these more computer science examples where you maybe have a one-to-many or many-to-many correspondence? So in what sense can we use the SIP to also tackle these relational results or related types? Yes. Right. So now let me quickly give you a little example. So if you want to represent finite multisets, you might define an interface with an empty set, insertion, membership, union, intersection, and so on with suitable axioms. This can be implemented using lists, for example, or more efficiently using association lists. So it's essentially an element is paired with its multiplicity in the multiset, right? So I gave a very simple example here. So this 1 minus 2, 1, 3, 1, 3, minus 5 would be represented up to permutation as this list or this association list. So 1 occurs 3 times, so we have it as 1, 3, and so on. So yeah, you see these two types are possible implementations of this simple interface for finite multisets. And of course, if you have a very big set with a lot of repeated elements, it's much more efficient to store things with their multiplicity instead of storing them as many times as they occur. So pretty obvious. It's kind of similar to the unary binary problem we had before, that this association list should be much more efficient to work with, while it's probably easier to prove things about normal lists. So same kind of thing. So these two types are clear in a many-to-many relationship. So the SIP doesn't directly apply, but luckily you can fix this using HITs. So here are two big HITs. So the first one is kind of simple. So you define a listed finite multiset. It's just like the normal list constructors, but then you also add a constructor that tells you can permute elements. Right? So it's probably, you believe me, this is a way to represent listed finite multisets. And then you can do the same for association lists, where you kind of pair an element with its multiplicity, but then you need a few more axioms. So for example, if A occurs, so you have like a swapping axiom here as well. And then you have, if A occurs with multiplicity M and multiplicity N, then it occurs with, then it's the same as having it with M plus N many times, and so on. So these two types are now in fact isomorphic. So what we did was we started with some kind of normal type, like lists, and then we added some higher constructors to both of the types, and then we end up with two types that are isomorphic. And this happens a lot. Like we have, for example, we have other examples of this, like queues or dictionaries and so on, trees. So this happens a lot. So what we asked then, under what circumstances can we make a relation between two structured types into an isomorphism like this? And this led us to this relational form of the SIP, which I'll show you in a minute. Yeah, I should have a few more minutes, right, Peter? So yeah, good. Right. So, okay, so the relational SIP, that's the last thing I'm going to show. So first of all, we use this notion from the literature called a zigzag complete relation. So we want to start with some kind of heterogeneous relation. So a relation between two different types, and it should be proposition valued. And then we have this kind of funny looking condition. And it gives us this kind of zigzag. So we have, if A is related to B and A prime is related to B and A prime is related to B prime, then we get the dashed line here. And this is kind of a way of approximating what it means for a heterogeneous relation to be symmetric and transitive. So that's the intuition behind this definition. So we start off with that. Then we also, so then we had another notion, which is a quasi-equivalence relation. This zigzag complete relation. So it's almost, well, it's an approximation of a symmetric and transitive relation, which is somehow tracked by functions like this, where a function from A to B, such that for any element A, forward of A, so if we map it over to B, then R is inhabited by this, and the same in the other direction. So this kind of gives us the reflexivity part that is needed to turn the thing into some form of equivalence relation. Right. And then, yeah, I add some notation. So this induces a relation on A and a relation on B, kind of the obvious way. So you map some, yeah, well, this thing. This by these two axioms or these two assumptions, this will be reflexive. And then we can prove that these two induced relations are in fact equivalence relations, and that this two maps back and forth actually induce an equivalence on the quotient types like this. All right, so now we have a good notion of relation which induces the desired equivalence on the quotient types. Then we also have to take into account structures. So we say that a relation is structured if it somehow lifts, well, for structure S. So if we have a relation between A and B like this, on A and B like this, it should lift to a relation of structures between A and B, like structures on A and structures on B. Right. That's pretty, yeah. And this combined with what I had on the previous slide, let us sketch the main statement of the work, which is this relational version of the SIP. So if we start off with such a structured relation, which is suitable, this is a technical condition which I didn't put on the slides, but you need some extra assumptions, okay? And you have two structured types. Then for any quasi-equivalence R, which is structured by some, well, S and T, yeah, R in rho, then you can get induced structures like this on the quotient types, which are related by this rho according to the equivalence on the previous slide. So it's a bit hand-wavy maybe, but hopefully the idea gets across to you. So if you want to look up all the details, we have a paper on the archive where you can find everything. And what is very nice about this is that it's also modular in the same sense as the SIP I showed earlier. So proving that some structured relation is closed under various typeformers, kind of you can prove that, and then you can automate many proofs also in this setting. Yeah, and we've applied it to two different examples for this paper. And right, so let me sum up. All right, so the SIP, which you saw, there are many different versions, but they're essentially about characterizing equality and sigma types, which can usually be kind of tricky. And this applies to a large class of I guess, single sorted the way we did it, but multi-sorted should, yeah, I'll mention that in a second. So yeah, so the proofs are very modular and can be automated using reflection and Agda. And we can then use this to transfer programs and proofs between structured types. Right, so now, so what we're working on now, so this, so you can form kind of a displayed version of this. So some of you know about Peter and Benedict's work on displayed categories, and Ulrich Buchholz and the student developed a form of displayed univalent reflexive graphs, which is really a kind of a displayed version of the SIP that I showed in this talk. And then you can also do this multi-sorted examples, for example, and many other things get, many other examples get kind of nicer. So we're currently working on making a displayed version of this in the library. Right, and then I want to do more examples, of course. You always want to do more examples, and maybe interestingly, my student Max is now working on kind of applications in algebra with a view towards algebraic geometry. So right now it's doing ring localizations. All right, so that was it, and I'm happy to take some questions.
Thank you very much. Yeah, right. Yes. Questions? Torsten Aldenkirch has his hand up.
Yes, thank you.
Hi, Torsten.
Yes, very, very interesting talk. I just try to download your paper, but it comes next. Thank you very much. Actually, I have two comments. I don't know. I maybe I should only make one, right? Out of fairness, right? My first comment is you talked about parametricity, and I thought there's an interesting observation that both parametricity and univalence sort of realize this idea that you cannot look into a type. The types are somehow abstract, right?
Yes.
And something which I find always a bit disappointing is that you cannot actually, I mean, okay, you proved a theorem which is related to parametricity, but in general, you cannot prove this parametricity principle from univalence. So for example, one consequence of parametricity is that anything which looks like any parametric function is actually natural. And that is something you cannot prove in HOT. So there's some incompleteness. Yeah, I don't know what your thoughts about this are.
Right. Yeah. So right. So univalence and parametricity are kind of they're related but different, right? So
yes.
And in some sense, it's maybe good that univalence doesn't imply parametricity, because parametricity is like, at least internal parametricity is anti-classical, right? So you can't, it refutes the
well, they're classical. I mean, the principle, for example, if you specialize this a bit, the principle that every polymorphic function is natural is true in the term model, right? So there should be no issue, no problem. But we don't know how to prove it, right? I mean, I have an idea, but in the end, that would be a different talk. But that's cool. Sorry, my second remark. Do I get away with this, Peter? Are you really angry with me? No, you smile. Peter smiles. Peter always smiles. This is
we have another talk we're waiting for, so less time pressure.
Okay.
Right.
Okay.
So you don't buy my answer, Torsten?
Sorry?
About it being anti-classical being a problem.
No, it's not anti-classical. I mean, if you formulate it the right way.
Okay. Well, most formalizations, ways to express it I know are anti-classical.
Okay.
So
I think we have to take this offline. It shouldn't be, obviously, the parametricity shouldn't be anti-classical. If you do it the right way, it's not. That's it. Okay.
Okay.
I mean, no, look at this. Okay, look at this.
Shall we move on to the second comment?
Yeah, okay.
Second.
Yes,
okay.
Yeah,
Thank you. Peter's getting annoyed. He still smiles.
I'll cut you off on your first comment, and you can have your second one.
There's annoyed smile now. Okay, sorry. So my second remark is, you highlighted one way to use cubical theory in set-level mathematics, and that was very well done. This is a structural identity principle. But for me, one thing which really got me excited, and you know this, is this broken symmetry in conventional type theory, where we have inductive definitions and they all work out nicely, and we can reduce, so induction and recursion becomes one, and this is really, really cool. But then when we go to the other side of the mirror, co-induction and co-recursion, they don't really work together very well. And once you move into this cubical world, this asymmetry, this broken mirror disappears. And I think it's really, truly beautiful, and deserves to be emphasized.
Yes, I totally agree. As far as I know, there are, I mean, we mentioned it in the Cubical Agda paper that it's useful, I mean, very briefly, but I think, yeah, it definitely deserves a paper on its own, and people developing some kind of nice theory using co-inductive types in Cubical Agda. Yeah. Maybe you're doing that right now, Torsten.
No, it's very difficult to write a paper about some observation, you know, it's difficult to turn it into something concrete. I mean, I use it in my teaching and so on, but it's, yeah, I don't know.
Yeah, maybe it could be a proof pearl or something. Yeah. Anyway.
Yeah, that's true. Yeah. That's true.
Mm-hmm. Yes, I agree. Yes.
Any other questions from people non-equal to Torsten? I have not exactly a question, but a comment, as ever. the formalization by Eric of setoids and the connection to set theory in Agda that Anders discussed several times, that is available. I'm just posting the link to the chat. So that and other things that Eric had made public or made partially public and intended to make public, I'm rehosting them on GitHub. So that's the only one I've actually rehosted so far. But anything else that a formalization that he had been sharing with people public, sort of semi-publicly, if there's anything anyone would like to see publicly available, I'm happy to put them up on that archive. So let me know. So this formalization is up there. Unfortunately, it doesn't compile, and it's quite difficult to get it to compile. I know that Guillaume had sat down with Eric for a bit before Eric Smith, trying to get it to compile over a fairly recent version of Agda. So I'm not sure what version of Agda Eric had been most recently using on it that it did compile with.
Oh yeah, that was in my email that I, yeah.
Yeah, if anyone does feel up to the challenge of taking it on and trying to update it to get it to compile, then again, that would be very welcome. It would be lovely to see this taken over and maintained and maybe developed further.
Yes, I totally agree. So it would be very nice.
So, yes, any other questions? All right, then if that's it, let's thank Anish again for a very nice talk and take lunch.